Hello everyone. In previous video, we talked about one method of the numerical integrations, that is Gauss-Legendre rules. As a general, numerical integration is used to estimate the area under a curve when finding the exact integral is difficult or when we only have measured data instead of formula. For this reason, instead of to take it in to solve and finding the answer of the integrals based on the calculus knowledge, we are evaluate this function at the sum points, that is called quadrature points. And for each of these quadrature points, we have a weight associated. And depends on the type of the equations, the type of the method, we are evaluate a function directly at the sum points and multiple to the weight. And we can estimate the answer of the integrals. As a general, we have three main categories for solving the problems. The first category is a Newton-Cotes method. Another category is a Gauss rules. Gauss quadrature methods. We have a different method for the Gauss rules. And in last video, we talked about only the Gauss-Legendre rules. These rules optimally integrate the polynomial functions if we are talking about if we focus to the Gauss-Legendre rules. This is optimally integrate the polynomial and on an interval of the -1 and 1. And why we say is a Gauss-Legendre? Because the Gauss invented the method, and the name of Legendre is due to the fact that the location of the quadrature point are the zero of the Legendre polynomial's functions. And depends on how many points we are selecting. For the Gauss-Legendre rules, we can increase the order of the polynomial function. For example, if we are using the just one point of the Gauss-Legendre rules, we can find the exact value of the integral for polynomial of order 1 and below. And for the 1 points, we are evaluate f of x at point 0, and the weight associated by this quadrature point will be 2. It's meaning if we have this integral f of x dx, instead of to take an integral directly from these functions based on the calculus knowledge, we are evaluate this function at point 0 and multiple to the 2. Because based on these equations, for the 1 points, we have w f of x naught. For the 2 points of the Gauss-Legendre rules, we can find the integral of the polynomial functions with order 3 and below exactly. And again, on an interval of the -1 and 1, for the 2 points of the Gauss-Legendre rules, the weight for each of the points of the quadrature point will be 1, and we are evaluate a function at these 2 points. This is for the 2 points. As you can see, the W1 and X1 for the 1 points and W1 and X1 for the 2 points, the value are different. For this reason, then depends on how many points we are selecting. We are the value of the quadrant and the value of the weight will be changed, and also we have to evaluate the quadrature. We have to evaluate a function at the different points, and based on this equation, 2n minus 1, if our function as a polynomial function, we can find the exact answer of the integral with polynomial 2n minus 1 and below. But this is, as you can see, these equations from the interval of this integral from -1 to the 1. But how we can apply or use the Gauss-Legendre rules for the general intervals? We are doing the linear mappings. For example, if we have these functions, if we are trying to find the answer of this integral based on the Gauss-Legendre rules, we have to rewrite this equation or transform these equations to the standard intervals for this. So it's meaning -1 to the 1. And how we are doing? By linear mapping. And the equation for linear mapping is b minus a over 2 xi plus b plus a over 2. For this integral, the a is 2, the value of the b is 10. We have 10 minus 2 over 2 xi, 10 plus 2 over 2. And the answer is 4 xi plus 6. Also, for transferring the dx to the dxi, we are using the Jacobian. And what is the equation of the Jacobian? Is b minus a over 2. For these examples, we have 10 minus 2 over 2 equal 4. Now, by this linear mapping, we can rewrite this equation from -1 to the 1. Okay. Now we have -1 to the 1. Instead of the x, we write this equation. We have 4 xi plus 6 squared. The sine 4 xi plus 6. And how about the dx? Is Jacobian times dxi. We can write this one here. Dxi. Now, based on how many points, okay, for example, by 1 point, 2 point, 3 points, and so on, okay, we can estimate the value of these, the integral of these equations. And for the Gauss-Legendre rules, okay, we never evaluate a function at the -1 and the 1. For this reason, this method is called as the open rules. And we can apply these equations or this method for the singular endpoints. The maximum number of the points that we are evaluate in this range from -1 to the 1 is 96. This is about the briefly summary from the last session. Now we are talking about the second group of the numerical method that is called Newton-Cotes method. In the Newton-Cotes method, we have three methods: trapezoid, Simpson, and midpoint. And now we are trying to we are trying to understand how we can find each of these equations. Okay. The Newton-Cotes formula commonly used when function data are provided in tabular formats. Alternative to the Gauss integration, which require we are able to choose location of quadrature points. Today I will talk about the basic Newton-Cotes method, and after that I will talk about the compounds rule. The basic notation is to replace the f of x by a function we can integrate exactly term by term. We can estimate the f of x by Legendre interpolations or Lagrange or Taylor series. First, we see the trapezoid methods, okay, and we can say, before I show the trapezoid method, one approach is to approximate our function by Lagrange interpolation polynomials, and the simplest rule is a trapezoidal rules. For trapezoidal rule, okay, we are using the linear Lagrange interpolations. Okay, in this method, we take the 2 points, x0 and x1, and with their corresponding function value is mean the f of x0 and f of x0 and f of x1. We connect these 2 points with a straight line, and that line represents the linear Lagrange polynomial that approximate the functions between the x0 and x1. Okay, and how about the h is a difference between that is called a step size is equal x1 minus x1. This is about the linear Lagrange interpolation over these two data points. This meaning between the x0 and x1. And now we have these equations. Based on this equation, we are evaluate a function at the x0 and x1. This means x0 and x1 as a quadrature point. And this is these coefficients, okay, is a weight associated with for x1 and x0 and x1. And this is about the error, because as we know that this is the approximate method. For this reason, we will have a error for or truncation error for this method. How we can find this value in a simple terms or based on the A and B? Okay. And we replace the x minus x1 with a new variable t. So that the dx equal the dt. Also, if we let the x0 as a edge and the x1 equals 0, then the limit of the integral change accordingly from x naught to x1 into the h to the 0 for the t function. And when we do this substitution and simplify the integrals, okay, we can find the value of the W naught and the top W1. And as you can see, the value is the half of the H or half of the step size. And what is the H? Is a difference between the B and A, or X1 and X0. Okay. And this is the equations. This is the basic trapezoidal rules. We have the half of the edge, or the half of the step size, times the value of the function at A plus the value of the function at point B. As you can see, we are evaluate a function at these 2 points, is meaning at the point A and B. For this reason, this method is as a closed quadrature formula, and the truncation error for this method approximately as a h cube. This method, by this method, we can find the exact answer of the linear functions, okay, and we denote this as a t sub 1. The T is a trapezoid. The 1 is shown as a single trapezoid. Okay. We can use the higher order methods for getting better answer. Okay. One of the examples is a Simpson method, okay, in which is based on the quadrature Lagrange interpolation. As you see in the previous slides, in trapezoid method, we use a straight line to connect the 2 points and approximate the area under the curve. But here we will use the parabola and that pass through to these 3 points, x0, x1, and x2. And we connect these 3 points together, okay, and we are find the area under this graph. For this reason, the Simpson rule is more accurate than the trapezoid. And yeah, another things we have to know that the distance between each point is h, okay? And how we can find the h for the Simpson rules is found by b minus a over 2. And again, the Simpson rules is found based on the quadratic Lagrange interpolations, and we can find each of these components, like as the trapezoid, and this is the answer for the Simpson rules. And we can find the answer of these integrals based on this equation. We have to evaluate a function at the x0, for this one as a times 1/3 of the h, plus evaluate a function at the x1 times this weight, plus value of the function at point B times this weight. And the amount of the truncation error for this method, h to the power 5, approximately as a h to the power 5. And this method is called Simpson rules. And as you can see, we are evaluating a function at a and b. For this reason, this is as a closed quadrature formula. And we do this as a S sub 1. S show the Simpson, and the 1 is show we have a single Simpson panels. We can increasing the Lagrange interpolations, okay, cubic, order 4, and so on, okay. And all of these methods as a closed Newton-Cotes formula, but we don't typically use the higher order rules because of potential for oscillation in higher order of the polynomials. Usually we don't apply the trapezoid or Simpson rule just once over the entire intervals because that would give a rough estimate. Instead, we divide the interval into the several small sections or several panels and then apply the same basic rules on each panels. For this reason, this approach that we try to make a more panels or try to make a more segments under the graph is called compounds rules. Now we will see how we can write the compounds rules, how we can apply the compounds rule for trapezoid and Simpson methods. Okay, this is the compound trapezoidal rule. Okay, and we learned that to get a more accurate estimate of an integral, we can use the compounded trapezoidal rule. Instead of approximating the entire interval with a single trapezoid, we split it into n equal subintervals, each panels or each of these subinterval has a trapezoid. And then we added all of these area together. And the equation, as you can see, the value of the step size will be changed. We have a b minus a over n, depends on how many panels you wanna create under the graph. And we can address each point's entire of this graph by this equation, a plus jh. If you are trying to find the x sub 2, we have a plus 2 times h. By these equations, we can find the value of the x sub g. Okay, if you look at these equations, we have, based on this equation, we have the summation of, we have the value of the function at point A and at point B, but for any points between the A and B, okay, we multiple to the 2 because each point, okay, is calculate 2 times. For example, if you are trying to find the answer of these 2 trapezoids, as you can see, the x1 is common for these trapezoid and the next trapezoid. For this reason, we have a 2 times all the points between A and B. This is the equations for the compound trapezoidal. The next one is the Simpson rules. Okay. For the Simpson rules, okay, we look at 2 subinterval at a time because we need 3 points, okay, to draw a parabola that fit the curves. And each pair of subintervals share a middle point, and the rule uses these 3 points to approximate the area under the curve. That's why the n must be as an even number. And the formula, and if we look at the formula adds the first and the last function's value once, okay? And then multiple the odd points by 4 and the even points in between by 2. And this is the equations for the compound Simpson rules. And the edge or step size for the compound rule is find based on this equation, b minus a over n. And again, the n should be as an even number. And we denote this as a S sub n over 2, that is composite Simpson rules with associated error sub n over 2 error. These are closed rules as they require to evaluate a function at a and b. For this reason, we cannot be applied with integrand with singular endpoints. Another method for the Newton-Cotes method is a midpoint. The midpoint is another method to approximate the integral by evaluating the function at the midpoint of the interval rather than the endpoints. Is meaning in these methods, we are evaluate a function at the midpoint. We are not evaluate a function at A and B. For this reason, this method is called as the open rules. And we can find these equations by Taylor series, or by expanding a Taylor series about a midpoint. And we have f of x naught plus the derivative of the x naught times x minus x naught. And the derivatives, okay, for these integrals, the integral of the derivatives turns to the 0 because we have because the midpoint in the middles and we have symmetrics around the midpoints. And the answer becomes this. We have 2 times h times the value of the function at the midpoint. The error for midpoint approximately as a h cube, and we find the step size for the single midpoints by this equation, b minus a over 2. For midpoints, like as the 2 other methods, okay, we have a compound midpoints. And this method improves the accuracy by dividing the interval into multiple smaller subintervals and apply the midpoint rule to each one. And for each subinterval, we take the midpoints and evaluate a function there and multiply by width of the subinterval. Then we add add up all these contributions to approximate the answer, to approximate the total integral. By using the multiple subintervals, the method captures the shape of the function more closely because the 2 other methods, and the amount of error decreases as the number of the interval increases. Exactly, these rules is applied for the Simpson and trapezoids. And as you can see, for the midpoints rule, we are not evaluate a function at point A and B. For this reason, this method is called as an open Newton-Cotes method. And we can apply to integrand with singular endpoints. Look at these examples. Okay, the error functions. The value of the error function at point 1 has this value. When we are using the single trapezoid, single Simpson and one midpoint method, we find the value of these integrals. And the amount of error between the exact answer and the midpoint has a least value for trapezoid with one panel with the exact answer. This is amount of the error, and this is about the Simpson with single panels. This is a this amount of the error is high, okay, and we can improve or decrease the amount of error by increasing the number of the panels. For example, once we are using the trapezoids with two panels, the answer of the integral is become this, and the amount of the error for trapezoid with two panels will be decreased, because for trapezoid with one panel, the amount of error between the exact answer and this estimate is 0.07. For trapezoid with two panel is reduced to the 0.01. Once we use the 4 panels, the amount of the error become 4 times 10 to the negative 3. Exactly, we have these trend of the answers, okay, for the Simpsons. When we are using the one panel of the Simpson rules, the amount of the error is a 4 times 10 to the negative 4. And when we are using the Simpson with two panels, the amount of error decreased to 3 times 10 to the negative 5. As you can see, the amount of error for the Simpson with one panel is less than the trapezoid with one panels, because if you remember, for the trapezoid methods, we connect two points together with the linear Lagrange interpolations, but for Simpson rules, we are using the quadrature Lagrange interpolations. This is about these methods. Okay. Let's look at one example. Okay. For this integral, three to seven, find T1, T2, S1, and M. Okay. For part A, for trapezoid with one panels, the equation is half of the h, the value of the function at A, plus the value of the function at point B. For the trapezoid with single panel, h is defined by B minus A. For this problem, we have 7 minus 3 equal 4. 4 over 3. Now we have to evaluate the f of x. This is the f of x at these 2 points. The answer is 20.9. This is the answer of this integral based on the trapezoid with single panel. For part B, we have to find the answer of this integral with trapezoid with two panels. First, I write the general equation for compound trapezoidal rules. And for the compound trapezoidal rule, the H is find based on B minus A over N. N is talk about it show the number of the panels. But for the single panels, we have the H equal B minus A. And X of J is found for A plus JH. For this problem, we have 7 minus 3 over 2. The answer is 2. And once we write the equation for trapezoidal with two panel, H over 2, the value of the function at point 3 this is the f of A plus 2 times the value of the function. Okay, this is 3, this is the 7. And we have to find the value of the function at this point. We have x1. If we consider this is as the x0, the x1 is 3 plus 1 times the h is 5. It means we have to find the value of the function at point 5. And the last point, the value of the function at point 7, f of b. The answer of this integral with two panels will be 20.40. This is the answer of the part B. For part C, we have to use the Simpson with single panels. The equation is the equation of the Simpson with single panel, f of x0, 4 times f of x1, f of x2. The h for the single panel of the Simpson is found by b minus a over 2. Is 2. And what is the value of the x1? The x1 is a plus jh. 3 plus 1. How about the h? Is 2. And how about the x2? We have 3 plus 2 times 0.2. The answer is 7. Okay, as you can see, we reached to the upper level of the integrals. Okay, is meaning this is as a f of b. answer for the Simpson with single panels is 20.5968. And the last part of this question is find the answer of this integral based on the midpoints method. The midpoint is the equation of the midpoints is 2h f of x. The h is defined by this equation, 7 minus 3 over 2 equal 2. And this is our interval. And we can say the midpoints for this interval is 5. 2 times 2. The value of the function at point 5 is 20.8. As you can see, for the midpoints method, as the open rules, because we are not evaluate this function at point 3 and 7. But how about the rest of the methods, trapezoid and the Simpson? As you can see, we are evaluate a function at the lower and upper level of the integrals. For this reason, this method is called as a closed rules. Okay. This is the summary of this lecture. For the Simpsons and compound Simpson quadrature rules, we learned that this is as a closed integration rules, and we cannot use this method for an integrand, singular endpoints, and the truncation error for the single panel of the Simpson approximately as a h to the power 5, and for the compound Simpson rules and the truncation error approximately h to the power 4. And for a single Simpson rules or Simpson panel, the step size is found by this equation, b minus a over 2. For the trapezoids and compound trapezoid quadrature rules, we cannot apply this method for the singular endpoints because this is as a closed rules, okay? And we have to evaluate a function at the lower and upper level of the integrals. The truncation error for the single trapezoid approximately as a h cube, and for compound trapezoid, the truncation error approximately as a h squared. For the single trapezoid, the step size is find based on this equation, h equal b minus a. This is about the another methods for the Newton-Cotes method. The midpoint and the compounds midpoints. This is as a open rules, okay, and we can apply these methods for the integrand with singular endpoints. And the truncation error for the single panel of the midpoint approximately as a h cube, and truncation error for the compound midpoint approximately as a h square. And the panels for the single panel, h is equal b minus a over 2. And the last method is the Gauss quadratures. And in this class, just we talk about the Gauss legendary rules, okay? And if you remember, for the Gauss legendary rules or some other methods, we are not evaluate a function at the endpoints. For this reason, this is as the open rules, and we can use for integrand with the singular endpoints. And by these rules, the Gauss-Legendre rules, we can find the answer of the integral of the polynomials up to n 2n minus 1 exactly. This is the summary of this lecture. Thanks for watching.